So the next thing we want to do is build up to this idea of a bijection. So the bi refers to two. So there's two parts to this. One is an injection, two is a surjection. So we're going to look at those two parts and look at what it means for a function to be injective or surjective. So bijections are very useful because if you can define a bijection between two objects, then it basically tells you that they're not equivalent, but they're very similar. So I mentioned earlier when we were talking about sets and cardinality that if you can make a bijection between two sets, then they're said to have the same cardinality. You can do this in a lot of different ways. Usually you need like a little bit more. Like there's another thing called a homomorphism. And if you can define a homomorphic bijection between two things, then it tells you that they're, I don't want to say equal, but for all intents and purposes, the same thing in certain contexts. So bijections are a very common thing that we're looking for between two different sets, really. It's going to be between two sets. So that'll tell us that the sets are very similar if we can make a bijection between them. So relevant in probability, of course, because we're just always dealing with sets in probability because of the sample space. So first we're going to look at an injection. So we'll first define this, and this is going to be something that is also not really new. So let f from A to B, that's kind of a sentence, even though it doesn't look like one. Let f be a function from A to B is usually how this is read. The function f is called an injection if for all x1, x2 and A, x1 not equal to x2, then f of x1, or I'm sorry, this should say if x1 does not equal x2, then f of x1 does not equal f of x2. Okay. So you might recognize this as a one-to-one function because that's exactly what it is. It's just another name for a one-to-one function. Okay. So it is also called a one-to-one function. So just a new name for it, basically. If you remember, one-to-one functions are very important because they're invertible functions. And like I said, you start using invertible functions kind of a lot in higher level probability. So it's important for us to know whether the functions are one-to-one. A lot of the functions you use in probability just kind of are by default, like the CDFs and stuff, at least on certain parts of its domain. So this definition, it kind of gives us a framework to actually prove that something is injective. So for example, if we look at the function f of x equals x, well then we say, okay, assume x1 does not equal x2. Then f of x1 equals x1 because that's the definition of the function. And f of x2 equals x2. And then since x1 does not equal x2, f of x1 does not equal f of x2. Okay, so this tells us that this function is indeed injective. Okay. Now, if something's not injective, I've kind of glossed over what do we do if you know, I've shown how to prove things, but what if we want to show that something's not true? Well, you just have to give a counterexample, right? If you can give one counterexample, then that means, well, that fits the conditions. That means, well, it's not true. So how do we show that this function is not injective? So here we can just say, you can do it a little generally, but you don't need to. You can just say, well, let x equal 2. Then f of x, let's say x1. F of x1 equals 4. Let x2 equal negative 2. Then f of x2 equals 4. So x1 does not equal x2, yet f of x1 equals f of x2. So this is not injective, okay, or is not an injection. So rather than dealing with the not equal to all the time, it's more common to kind of look at the contrapositive of this. Okay, so let's say note the contrapositive is if f of x1 equals f of x2, then x1 equals x2. Whoops. Okay, so it's a little bit more direct. You don't have to worry about the not equal to all the time. So I don't know, for example, we could look at, say, f of x equals 3x minus 7. Okay. F of x1 equals f of x2. Okay, we're assuming this. Well, f of x1 equals 3x1 minus 7. F of x equals f of x2 equals 3x2 minus 7. Okay, so now you add 7 to both sides. So you can do, it gives you a framework to kind of just do some algebra here, which means 3x1 equals 3x2. Divide 3 on both sides. So this implies x1 equals x2. Okay, so it gives you a way just to get to this statement, usually just by doing some algebra. In the squared case, x squared, you would take the square root of both sides, you would end up with a plus or minus. So then you have x1 equals plus or minus x2, which is not the definition, right? So now let's take a look at the definition of a surjection. So this is not one we've really looked at before. We looked at the one-to-one function, but we haven't really looked at this before. Okay, so let f be a function from a to b. F is called a surjection. Put this as a definition. Provided that the image of f equals the codomain of f. Okay, so what this means in terms of sets, or in terms of elements of the sets. So this means that for every y in B, which is the codomain, there exists x and a such that f of x equals y. Okay. So this gives us a little bit more of a framework because we can pick a y and b and then show that there must exist x and a. where f of x equals y. Okay. This is also called an onto function. Okay, kind of a weird name, but it's very common. Because f maps A onto B. Okay, so that's the logic there. So it's like it's covering the entire codomain. Okay, with your with the image. So f takes every element of A, maps it onto every single element of B. So it's like it's covering it. So you're putting A onto B. This one can be a little bit trickier to show directly, at least in my experience. Injective just kind of flows a little bit better. We can show that f of x equals x squared is not an onto function, or not surjective. Again, we can let first of all, we should just say, f is from R to R. So take, I don't know, -2 in R, which is the codomain. There's no x in R, which is the domain here. They're the same thing, but we're thinking of the different ones. Such that f of x equals -2. Okay. So this is not an onto function. So what is an onto function? Well, simplest example again would be f of x equals x. Right here, f is defined from R to R as well. So we know that the range, as we would formally call it, is the -infinity to infinity. Codomain is the same thing. So we should be able to show that it's a surjection. So take y and R. Then f of x equals x equals y maps to y. Okay. So in other words, whatever element you just took out of R, take the exact same element out of the domain, and that's going to map to y, right? And this is fine. The domain and the codomain are the same thing here. So whatever this element x is, it exists, right? So it looks a little bit funny. I feel like a lot of times when I'm proving something is a surjection, I feel like I'm not really even doing anything. I'm just like stating something that looks obvious, but it can be a little bit more tricky. It's definitely, it feels a little bit easier to prove that something's not a surjection, or at least it feels like you're doing a little bit more. So if we want to do something like 3x minus 7, okay, where f is from R to R. And by the way, like the codomain doesn't always have to be R. Like you could define x squared such that the codomain is only the numbers from 0 to infinity, and then it is a surjection. It's just not something that's typically that interesting unless you're like restricted to that from the problem that you're working on anyway. Like ideally you want the function to cover like everything that would be reasonable. So if you're only working on something that would only reasonably be positive anyway, then maybe that's how you define it, and then it's a surjection. So I'm just going with the most general form here for these ones, but you will see problems formulated that way because it can be from any set to any set. So let's go ahead and do this one. So take y and r. Then we need to find f of x that equals y, right? Which would imply that 3x minus 7 equals y. Well, this would imply that 3x equals y plus 7, which would imply that x equals y plus 7 over 3. Okay, kind of the same property as when you're doing inverse functions in a way, when you're finding them. So does this element of x that we just found, x where x is equal to y plus 7 divided by 3, does that exist in the real numbers? Well, yes, it's guaranteed to, because y is also in the real numbers. It's just any real number. You can add 7 to a real number. You can divide by 3 in the real numbers, and it's still going to be a real number. So this element x does exist in the domain. Okay, so this is an onto function. Okay, so we could say this, which is equal to r, which this set right here is referring to the set that is our domain. Okay. All right, so finally we'll define a bijection. So a bijection is both an injection and a surjection. Okay. So we just need to check both of those things separately, basically, that something's an injection and a surjection. So let's go back to that example I was using between the sets, right? Where we have the natural numbers, which is 0, 1, 2, 3 to infinity. And then we have the evens. Sometimes this would just be called like, it might be called like 2n or something like that, which just kind of represents multiply all the natural numbers by 2. But let's just call it the evens. Okay. So this would be 0, 2, 4, 6, etc. So I mentioned that we can define a bijection between them by multiplying every element by 2. So let's try to formulate that a little bit more now. Okay. Let's let E for evens be the set of n and n such that 2 divides n. Okay. So this is the set of even numbers, right? Maybe we could formulate it as instead n is equal to 2 times k, where k is an n. So we can define f from n to e by f of n equals 2n. Or you could use x, but n is just commonly used with the natural numbers here. So we would need to show that this is a bijection by showing that it's injective and it's surjective. So we can do that. So injection, assume f of n1 equals f of n2. Then 2n1 equals 2n2. Divide both sides by 2, and then you get n1 is equal to n2. Okay, so it is an injection. Is it a surjection? Okay, so we want to take, let's say, y in E. Okay, then we want to find f of n, which is equal to y. Okay, So f of n equals 2n equals to y. This implies that n is equal to y divided by 2. So y came from the even numbers. If we take that y, the even number, and we divide it by 2, we will be left with an element in the natural numbers. Okay, so this is guaranteed to exist. So this n is definitely in the natural numbers, so we have found its corresponding element here. So this is a surjection. So therefore, this is a bijection, which in terms of sets is important because it tells us that they have the same size. Okay.